I'd like to welcome you to this short video series in which we will work together to complete the 3 guided experiments found in your Launch experiment kit. In just a few seconds, there will be a table of timestamps here so you can easily navigate the course. I'd also like to use this time to introduce myself. My name is Nolan Tremelling. I'm a student at Columbia University and am majoring in electrical engineering. I'm going to be here to help guide you through our experiments today. In this course, we're going to be exploring 3 unique experiments. First, we'll learn how to use our launch kits. To do this, we'll start by exploring the basics of electricity and circuitry. Together, we'll create a light show. Then, once you're ready, you'll be able to create one of your own. Then, we're going to explore greenhouse gases. Together, we'll learn what greenhouse gases are, and then we'll create a closed model to see how they affect temperature. Finally, we'll grow a plant together. We'll use the techniques that we learned in our first 2 experiments to model and predict how our plant will grow. Before we get started today, it is important to note that you must set up your Nebula Education board. To do this, you can follow the board setup page on our website. You can access this at nebulaed.com/setup. Once you have your board set up, you're ready to continue to the next step. Let's get started with our first experiment using LED lights. For this experiment, we'll be using 1 Nebula board and data cable, 1 breadboard, 3 LED lights, and 6 type AA wires. In this picture, we can see the Nebula board in the center. It's a dark blue board with input and output pins. The breadboard is going to be the light blue board on the left side of the picture, and this only has input pins. The 3 LED lights can be any color that you choose out of your kit, and the 6 type AA wires are going to be the wires that have 2 sides with metal coming out. This is compared to the type AB wires that we'll use in later experiments that have only 1 side with metal coming out and 1 side with metal going in. Before we get started, let's look at what a circuit is. A circuit is going to consist of a source and an element. In this drawing, we can see that our source is a battery, but it could also be a nebula board, and our element is our LED light. When our source wants to deliver electricity to our element, we have to make sure that it has a complete closed circuit. This means that the electricity going from the positive side has to connect to the negative side. It's important to know that we can't just connect the positive to the negative side, because if we do that, we create a short circuit, and this is bad. What we have to do is we have to put things in between. This is our element, our LED light. So what happens is when we pass the positive electricity through the LED light to the ground, which is our negative side of the battery, the LED light lights up. Here we can see a drawing of an LED light. At the top, we're going to see the bulb, and we're going to see 2 prongs coming out of this. The longer of the 2 prongs is called the anode, and that takes the positive energy, and the negative is called the cathode, which takes the return. It's important to remember these because if you switch them and give the cathode the positive electricity and the anode the negative electricity, our LED will not light up. One way you can remember this is someone who thinks of cats negatively is going to relate to the cathode, the cathode. When we supply power to the positive side, the anode, and return it to the power source through the negative side, the cathode, we'll see that our LED light lights up. And before, we should look at what a breadboard is. So our breadboard is going to be a bunch of connected pins, and as we can see here, the pins are connected horizontally, so across. And on this breadboard, we're going to have 2 columns. The pins across these columns are going to be connected, but the 2 columns are separate from each other. So we can put multiple connections into a row, but we have to remember that once we put a connection into this row, it's either going to be a positive or negative row. We can't connect both at the same time, or we'll create a short circuit. Now, to set up our board, what we're going to do is we're going to place the 3 LED lights into different rows of the breadboard. Then, we'll be connecting the positive side through our output pins on the board using pins 2, 3, and 4. and then we'll share a common ground, a negative or electricity return, to the ground pin on the nebula board. We'll look more closely on the next slide, but this just gives you an overview. So if we look closely, we can see here that we have the 3 LED lights. In the picture, you can see that the green and the blue dots underneath the LED lights are what are connected to each other. These are the horizontal rows of our breadboard. And it's also important to remember that we have to make sure that we connect the longer side, the anode, and the cathode, the shorter side, to the correct terminals. So remember, the anode is the positive and the cathode is the negative. As we can see, the cathode, the negative sides, are all going to share a common ground. So we can go from the yellow to the blue and from the blue to the red, which then goes back to the ground on the nebula board. This is just going to tie all of them together and make a nice clean circuit board for us. We can't do this with the positive, however. So what we're going to do is we're going to give each of these their own power supply. This is all shared so it doesn't create a short circuit. And what we can do from there is go from pin 2 to the yellow, pin 3 to the blue, and pin 4 to the red. And when we give power to each of these, we'll see the LEDs light up. Now, we'll look at a little bit of code for this, but we aren't going to go into too deep of an exploration to code in this experiment. But what's important to know is that when we're programming our nebula board, we're going to use Arduino software. So let's look at this. Inside of our code, we're going to have variables, and this is where we declare our variables in this first block. In the first block where we see int red, int blue, int yellow, this is where we're going to tell the board what color LED and what pin they're connected to. So our yellow is connected to pin 2, our blue is connected to pin 3, and our red is connected to pin 4. To do this, we have to declare the type. So our variable, the thing that can change, is the color of the LED, which we've just named red, blue, and yellow. The type that this is an integer. Integers are whole numbers, so like 1, 2, 3, 4, 5, 100, 1,000. So this is how we name variables using the Arduino software. Int for integer, our variable name, in our cases, red, blue, and yellow. And then we're going to use an equal sign and declare what pin it is. And then to end that line of code, we need to put a semicolon. Now, it's important to know that when we're programming in C and C++, which is what the Arduino software uses, that we also have to have 2 different loops. We have a void setup and a void loop. Void setup is always going to run at the beginning of our code, and void loop is going to run over and over and over again. So void setup runs once, while void loop runs until we turn our board off. Inside of void setup, we need to declare a few things. So we're going to write pin mode to tell the board what kind of output we're using for the pins. And within here, we need to have a few parameters or different things that we can change. So we're going to have pin mode, and then we're going to tell the computer which pin we're referring to. In this case, we can easily just say red, blue, and yellow. And then we have to tell the board if it's an output or an input. In this case, we want to use it to give power, so we're going to write output in all capital letters. Again, we need to end our code with a semicolon, so we're going to do that right here. Then we're going to go to void loop, and in void loop, we're going to go and run this over and over and over again. So when the code starts, we're going to have digital write as a function. And our digital write function is using that pin as an output pin, like we declared before, but it's giving it a value. So it's going to give it a value of low or high. A value of low is going to be 0, and a value of high is going to be 5. and this refers to the voltage coming out of the pin. So when we write digital write red, again referring to the pin, comma, high, we're going to be writing digital pin, the red LED, is going to get high voltage, which is 5 volts. Then what we're going to do next is we're going to wait 2,000 milliseconds. This is 2 seconds. And then we're going to write another digital write function, digital write blue, which refers to the blue LED, and high, again, to say 5 volts. Then after that, we'll have another delay of 2,000 milliseconds, or 2 seconds, to write digital write yellow, high. And then we're going to wait another 2 seconds. And what this does is it writes high across each LED, which is going to give a different amount of power at a different amount of time to each LED. And remember, we are just going to have to make sure that we put the semicolon at the end of all of our declarations here so that the code knows to stop that line of code. And the last important thing to remember is at the very, very top of this code, you're going to see a dash and a star. And those are just some comments. You can write comments into your code using that same style. This is stuff that the computer will not read at all. So now we can see that we've set up our board. We've connected our circuit in the breadboard to our Nebula board, and we've connected our Nebula board to our computer using the data cable. So when we run our code, we're going to see what happens. So we can see that our red light lights up, our blue light lights up, and our yellow light lights up with 2-second interval spaces in between. Thank you for completing your first experiment with Nebula Education, and let's move on to the second. For our next experiment, we'll be exploring greenhouse gases in a closed system. For this experiment, we'll need to create a personal environment. For this, we'll need one Nebula board and data cable, one TMP36 temperature sensor, one plastic cup lid, and 3 type AB wires. The TMP36 temperature sensor is a small sensor with 3 metal prongs coming out the bottom. We'll look at what each of these prongs do in the future. And 3 type AB wires are going to be the wires that have one side with metal prongs coming out and one side with nothing coming out. The side with nothing coming out is going to be used for metal prongs to go input. Also not included in this kit, but necessary for the experiment, is water and a sunny spot. Before we get started, what is a sensor? A sensor is a device that is going to measure physical properties, such as temperature, brightness of light, color, force, or pretty much anything else we can imagine. We can use sensors to incorporate what we experience in the everyday world into what our Nebula board experiences in our programs. Our TMP36 sensor is going to look like this. It's a half circle with one flat side, one rounded side, and a flat top. Out of the bottom, there's 3 metal prongs extending. Looking at the flat side for reference, we'll see that the leftmost pin is going to be our voltage input, the middle pin is our voltage output, and the last pin is our ground. What we can do with this is we can provide a known voltage to the voltage input. From there, we'll be able to compute in our code based on how much voltage is coming out, the temperature. This is given to us by the manufacturer of the temperature sensor because we can't calculate this necessarily on our own. It's important to know that we have to connect the ground pin to the ground in the Nebula board because we need to use this as reference. We need to find out how much voltage change there is in this circuit. So our TMP36 sensor takes a measurement of how much voltage is going in and going out. And from there, we'll be able to find our temperature. To set up our board, we're going to connect the voltage in pin of the sensor to the 5-volt output on the board. We'll then connect the ground pin of the sensor to the ground pin on the board, and we'll connect the voltage out pin of the sensor to the A0 analog 0 pin on the board. This is how we're going to be reading what the sensor's value is. Again, the 5 volts is providing a known voltage, the ground is providing a known ground state, and the V out, the voltage out, is A0 or analog 0, and that's what we're going to be measuring. To set up our closed system to collect the data, what we'll do is we'll put a little bit of water at the bottom of our plastic cup and put a lid on top. Before we put the lid on top, make sure you cut a small slice, a hole, in the top of the lid. It doesn't need to be anything big, it just needs to allow us to put the bottom, the wires of our TMP36 sensor through. So the black knob on the TMP36 sensor is going to be inside of the cup, while the wires are going to be sticking out. From there, we can connect the wires just like we talked about before and connect it to our board. Then we'll be able to put the board in a sunny spot and see what happens. Now, to collect our data, we're going to need to run the code, which we'll look at in a minute, in a sunny spot. The code is going to work by collecting data every minute for as long as we let it run. We could go on forever, but we don't need to. For this experiment, 10 minutes should be enough. From there, we need to read the output of the sensor in the Arduino serial monitor. You can see on the Arduino web IDE, you can access this on the right side. You'll see we have the monitor tab, which opens just to the left of our code. This is also where we'll be able to access files, get help, and share our code. For our actual code, we have a few different things we should look at. First, right after the initializing comments, we have int temperature read equals 0. This is the variable that we declare for our sensor input. This is our A0, our analog 0, that we looked at in the previous slides. We're declaring here that we're going to be getting a temperature reading, a voltage reading really, from our analog 0 pin. Just like with any other code, we'll go through our void setup and we'll begin the serial plotter. And then when we get to our loop, we'll need to declare some more variables. Again, we're not going to dive into this math here, but you can see that we are able to do basic math within the Arduino IDE. We're able to do multiplication, subtraction, division, addition, and we're also able to add some order of operations in there using parentheses. If you'd like to learn more about this code, there'll be a link in the description to a future video which will dive into this. Next, we have a number of commands that have a serial.print output. What this does is this prints in our serial monitor the following. We first see serial print and then quotation marks, voltage. This is going to print text for us to read. Anything that's in quotation marks, the double quotation marks like we see here, is going to be text. This is nothing that we're getting from the code. This is just something that we're typing in. So it's not a variable that we're referring to. Next, we have serial print voltage. Now we don't have quotation marks here, which means that this, unlike with the quotation marks, is not a line of text. What this is this is a reference to our variable above. This is a reference to how we read the voltage coming in on the TMP36 sensor. Next, we'll have a line of text in which we'll say the degrees Celsius, and then we'll read the degrees Celsius. Then we'll have a line of text saying degrees Fahrenheit, and we'll read the temperature in Fahrenheit. We then have a delay of 60,000 milliseconds. 1,000 milliseconds are in 1 second, so 60,000 milliseconds are in 1 minute. What we're doing here is we're waiting 1 minute before we repeat this block of code, which is going to give us the chance to let our system make a change. Now, once we find the change in temperature over 10 minutes, or 20 minutes, or even 30 minutes, what we want to do is we want to figure out what this data means. You'll see with your Nebula kit, you'll get a link to a Google Colab notebook. This is an interactive notebook that you can use at any time to visualize your data. You can also access it down below in the description, but you will need a Google account to make changes to the code. This is free to do, and it's necessary. Now, when we look at graphs, we have two axes, or variables. These are things that change. If we look at the graph to the right, we see that we have an x-axis on the bottom, and this is our independent variable because it doesn't change based on what we're measuring. For us, this is time. We see that the time is in months: April, May, June, July. We could change this, of course, and we could put 1 minute, 2 minutes, 3 minutes, 4 minutes. We could also put years and put 2020, 2021, 2022, 2023. So our x-axis is always independent of the other variable. Our y-axis, on the other hand, which we see vertically going upwards, is dependent on the x-axis. So here we can see temperatures over different months in two different settings. So as the months go on, it appears that the temperatures tend to get higher. So in this case, we could say that our temperature is dependent on the time of the year. Here you can see we have purple boxes over our x and y axis. And when we graph data, we need to plot it using a coordinate system. We can see this here as x comma y. So in our graph, we'll see our different points based on the month and temperature, our x and y variables. So the red dot here we see goes down to May and over to 25. So it looks like in May, our temperature is 25. Now, once we understand that, we can open our Google Colab notebook. From here, you'll find instructions on how to enter your own data and how to structure the notebook to fit your needs. Once you're ready, you'll be able to go to the top and click Runtime, and then Run All. This is going to run all the code that we need so that we can graph our data. When you do this, it will give you a warning because Google did not write this notebook, I did. It's stored on a different website, GitHub, which you can also access in the links below, but you don't need to worry about this step. You can click Run anyway. We're not going to track your data. We're not going to look at anything else like that. This just allows us to give everyone access to their own independent notebook. Now, when we graph our data and we follow all the instructions in the notebook, we'll see a graph with your data in yellow, like to the right, and we'll see real data measured from a greenhouse shown in purple. We want to make sure that we choose Runtime and then Run All to measure this data. If we don't do this, we won't see what happens over time. When we go through this notebook, you'll have the chance to edit the y and x axis. You'll have a chance to look at why the data is doing what it's doing, and you also have a chance to learn how to program this on your own. Make sure you check out the linked resources below, which includes more videos on greenhouse gases, how they work, and I will see you in the next experiment. Finally, let's get started with our last experiment. We'll be looking at plant growth. For this experiment, we'll need 2 plastic cups, 2 compacted soil pods, 2 pea seeds, and not included in your kit, but necessary for the experiment, is water, a sunny spot, and a dark spot. We found that a closet or a basement works best for this. It doesn't need to be completely dark, but just dark most of the time. In this experiment, we're going to explore the data that we can collect using a Google Colab interactive notebook. You can access this down below, but you will need a Google account, just like the last experiment. In this experiment, we're going to let it grow. We're going to continue to explore the idea of independent and dependent variables, and we're going to look at how we can affect a system and how we can compare the data that we've collected. We want to look at how we can make estimates with our data. Before we get started, let's look at what a plant is and what a plant needs. We can see on our diagram to the right that a plant needs a few things to grow: water, carbon dioxide, light, and soil. It's obvious that a plant needs water. Water is going to keep the plant hydrated, and it's going to give the plant the ability to move all of its energy around itself. Carbon dioxide is a little different. If we look at us as humans, we also use carbon dioxide in just a different way. We actually take oxygen in and we convert it to carbon dioxide through breathing. A plant is going to do the opposite. A plant is going to take in carbon dioxide and release oxygen. The soil gives the plant nutrients and holds its roots in place. It also allows the water to absorb up through the roots. And finally, light. What does light have to do with plant growth? It's not a physical thing that we can touch, like the water or the soil, or even the carbon dioxide, even though we can't physically see that. So the light actually allows the plants to go through an advanced biological process called photosynthesis. Now that's a big word, so let's break it down. We can break down photosynthesis, photo and synthesis. The word photo comes from the Greek word light, phos. And the word synthesis comes from the Greek word synthesis, which means to put together. So literally, our word photosynthesis means light putting together. Of course, this has really a different meaning. To us, this means that the plant is able to use light to put together energy. And this light is going to become a carbohydrate. So what is a carbohydrate? Carbohydrates are a chain of oxygen and hydrogen that are sugars. We're not going to look too deeply into what these are, but you can see it's a complex topic. So what happens if there's no light for a plant? Will it even grow at all? It's not going to be able to make the carbohydrates it needs through photosynthesis. So what happens? Now, if a plant gets a lot of sunlight, we can assume that it'll have a lot of photosynthesis occurring, which means that it will get a lot of energy. So will a plant that doesn't have a lot of sunlight get less energy? Will one grow more and one less? Will one of them even grow? To find this out, we're going to grow our own plants. To do this, we're going to place the soil pods into the plastic cups, and then add a tablespoon of warm water to each. When you do this, they're going to expand like crazy. You can see on the picture to the right the individual soil pods, and then next to it is the expanded soil pod. Make sure you do this inside of the cup, otherwise it might make a mess. Once they've expanded all the way, we're going to add the seeds to the top of the pod and add a little bit more water. Then, using a marker or tape, we're going to mark one plant with light and one with dark. This is going to let us make sure that we know the difference between the two, just in case they get mixed up. Next, we'll go to our Google Colab notebook, which is linked down below. This is going to have all the instructions to collecting our data, and to do this, we're going to look at measuring the plants every day. We'll use the same techniques that we did last time, where you can edit some of the data while keeping some of it the same. To run this, we'll do the same as last time. Click Runtime, Run All, and it might pop up with a message to say, just to confirm that it's allowed to run on your computer. Again, I was the one who wrote this. We've collected no data from you, and it is perfectly safe to run on your computer. Once we've collected our data and gone through everything, we can look at what our data says. What plant grew more? The one with light or without light? Also, did one plant grow a lot taller than the other? Was it a lot fuller than the other? Was it a lot stronger than the other? Do both plants look the same? Is one darker and one lighter? What other observations can we make here? Now, we could do this experiment lots of times to get lots of different data. But can we make any general conclusions? Do plants grow better without sunlight or with sunlight? Will a plant grow taller if it has more sunlight? Or will a plant grow shorter if it has more sunlight? Will a plant have more leaves if it has sunlight? That concludes our last experiment with plant growth. Make sure that you fill out the Google Colab notebook, which is linked below, to gain access to all of the data that we'll be collecting.